So, hi, I'm Jess. I'm a new PhD student based at Swansea University in the UK. So, as you can probably tell from my accent, I'm not from the US and also not originally from the UK. I've actually been based in New Zealand my entire life and have been at the University of Canterbury for the past few years. So, because I don't know pretty much everyone here, I thought I'd start off with introducing my research and industry background and how that has led into my involvement with the Juno Research Project and what we're hoping to do this season on the ice field, as well as with some cool new ideas for engineering research and development that could potentially be involved with the Juno work. So my background is originally in mechanical engineering, and this was a part of the Teoris Faculty Rapid Extensive Ice Something Aotearoa project. So this was a project based on the McMurdo Ice Shelf in Antarctica, so just along from McMurdo Station and Scott Base, the Kiwi base. And we were looking at developing new ice sampling systems, methods, and equipment that can be used to collect multiple samples at different sites and depths across an ice shelf. And this had the overall aim of creating enough data with a high resolution of ice physical properties that can be used to drive modelling and flow laws. So we had a big geophysics campaign as part of this project, as you can see up here. So lots of 25 megahertz GPR to look at the shelf structures. And we actually conducted this GPR by towing a sled behind a Haglin, so a track vehicle that was shown earlier. We also had lots of GNSS stations. So these stations were a new low-cost, low-power design that I'll touch on later. But we also conducted some transient electromagnetics, TEM, some continuous and discrete theories, as well as seismic surveys and full-hole geophysics using an optical teleview. So after this geophysics program, we also conducted lots of hot water drilling and ice sampling, which is where my specific master's research came in, with building ice sampling equipment that can be used within hot water drill boreholes. So this is the system we're operating here. So quite a small scale hot water drill, all manually controlled, but is quite common for many programs looking at deploying thermistor strings and other seismic equipment. So quite versatile from different kind of science interests. So I developed two systems that collected ice samples in hot water drill boreholes. And as it was alluded to in the earlier talk, hot water drill boreholes can be quite irregular and have quite variable diameters with depth. So this can be a result of drilling processes as well as ice properties. So any system that operates in a hot water drill borehole and needs to collect a sample must be able to expand and contract to account for that diameter variation. So this is my small system that clamps out and extends a rotating core barrel into the sidewall to collect small samples that are around 50 millimeter in diameter. So it's quite a compact system. It's only 125 mil wide, so 12.5 centimeters, about that tall. And this video shows that when it clamps out, there's some oscillation as it cuts, which was a minor issue we had in the field, which meant that as we're cutting sample, it fractured as we're collecting it. So this just highlights how the engineering, especially polar engineering, requires lots of different steps, but something like this can be easily solved and creates opportunity for small little add-on aspects to other large scale science programs. So if you're already hot water drilling, you can just do some testing at the surface while nothing else is happening. And this flows on to the second system that I built and tested, which is similar to standard electromechanical ice core drills. which are used significantly throughout kind of cryosphere research. And so you might recognize the bottom component of the system, which is actually an adapted Kovacs hand auger. So this has been integrated in with a motor and specialized anti-torque system. So this creates opportunity for changing the size of the core barrel as well as other different aspects. But the key development of this system is the anti-torque, which is the uppermost part of the drill, which provides the reaction forces that are needed when you're rotating a motor cutting into something. So it has these expandable arms and circular blades that are spring-loaded and get forced out into the borehole wall. So this feature worked really, really well, as you can see here, supporting all the necessary rotational forces as we're drilling down, which meant that we could collect multiple samples across different boreholes on the Murdo Ice Shelf, which I was absolutely stoked about. This system, specifically the anti-torque, could be integrated with any number of different borehole sensors and borehole drilling equipment. So I'm quite excited to bring that experience into working on Juno this year. This kind of flows into a bit more of my geophysics work and how that leads in. So I've been working as a geophysical engineer at a company called Southern Geophysical New Zealand. And if you're asking yourself, what is a geophysical engineer? I still couldn't tell you, and I was in this role for a year. But pretty much I was just working on numerous different surveys across New Zealand, and also was involved with developing new geophysical equipment, such as fiber-sized sources and multiple different seismic land streamers. So just a couple of quick examples of the work I did in this role. So this is an example of where we were looking at characterizing different areas of a farm for wind turbine positioning. So it's a combination of GPR, resistivity measurements and conductivity measurements to identify areas that would be unsafe. If you were to put a big turbine on there, you don't want the ground to collapse. So kind of just a combination of different techniques to come up with a more conclusive answer. And similarly, this was a survey looking at hydrological properties near a small stream and wanting to understand how much of that water is flowing through the ground. So once again, some more resistivity ERT and some seismic correction tomography. So this all leads me into my PhD project, which just started, co-supervised by Seth. And I'm going to be looking at measuring and modelling surface melt lake, in particular this lake in Icy Basin, which Renee introduced earlier. But every year it forms and unfreezes, develops in size over the summer, and can drain in the late season, creating this blistering and potential an uplift effect in the ice. So I'm really interested in where the water is going. Is it percolating laterally through the firn, or is most of it draining to the bed and affecting our upstream rivers and lakes? So there's going to be a few different techniques that I'll be using to help quantify these processes over the season and how they're changing with conditions and atmospheric measurements. So I'm using a drone radar system to look at the firn structure and how that is changing with melt, hopefully, over repeat time series. So to have a look at what's happening actually in the ice as well, identifying the layers with the radar system, I'm going to be using self-potential mesh methods. So this is going to map changes in the electric field, which indicates if water is flowing and where it is flowing between. And alongside these, I'll be also using transient electromagnetic system. So this will help identify potential water flow pathways in the subsurface, So more looking at greater depths and trying to understand if any of the water that is flowing down from the lake ends up in the subsurface. So these data are hopefully going to inform model development. So this would be an ideal kind of outcome for my PhD project, is to adapt this model that Sammy Buzzard have created for modeling surface melt lake development on an ice shelf. But these lakes clearly aren't on an ice shelf, they're dammed by nunatak and other exposed bedrock at the surface. So wanting to look at changing the boundary conditions, but to constrain and develop an accurate model, need quite a variety of different measurements. So that is where Juno comes in and being such a great resource, because not only can I collect lots of different information about the structure of the lake area, there is also data available from atmospheric systems and temperature systems that can all help inform this work. So it's really exciting upcoming work. And I thought I'd just finish on some other projects that I've been involved with in New Zealand, particularly more from engineering aspects and how technology development could be useful. So this is a kind of prototype stress sensor we've been developing at the University of Canterbury and University of Otago in New Zealand. So the concept is inspired by work that was actually completed in Alaska very many years ago, which used kind of pressure systems to measure stress states in the ice. So we've done some testing and kind of come up with essentially this cube, which we mount strain gauge rosettes to and freeze into the ice. And because of the material properties of the cube, we can calculate an inverted stress in the ice once it's frozen in. So these are a few photos from one of the student teams that have been working on it in Christchurch, New Zealand. So we've got the sensor up here frozen into the ice and in the centre here. And this is the testing setup and some preliminary results. So all the testing was conducted at approximately -25 degrees using this insulated cooling system. And we're able to find that the measured in ice stress based on the strain gauges and the material properties of the cube was broadly representative of the applied stress from the load frame. So that's a really exciting result, and hopefully in the next kind of year or two we'll be able to come up with something that we can actually test in the field. So really excited to see how that progresses. And finally, I thought I'd quickly touch on the GNSS low-cost positioning systems that I mentioned earlier. So this is one of the systems that we deployed on the Mamurdo ice shelf last season. So these systems have comparable precision to the expensive survey grade alternatives such as the Emlyn and Trimble systems that you all might be familiar with. However, we can manufacture and deploy them for a fraction of the cost. So pretty much everything you see here, so the tripod, surveying antenna, battery, solar panel, and Pelican case with associated electronics, can be put together for all less than around $500 USD, which is great in comparison to the prices of what some of the surveying equipment you might be familiar with are. So this work was led by Holly Still and Hamish Bowman at University of Otago, and it is all open source and partsless and code is available on GitHub. So yeah, another great outcome from our intelligent research project. So yes, I'll open, so it's quite brief, but to any questions on anything I've talked about, and thank you for having me. Yeah.
In some of your earlier slides, when you had the expanding
anti-talks at the
Yeah.
top with the modified Kovacs underneath. Do those anti-talks have like rollers on the outside so to help it slide?
Yeah, definitely. So, show the video. So it's quite hard to see here because the rollers I have in this configuration are really, really small because this was in kind of fully dense ice. But we can change the size through the fern. But these kind of circular pivots that allow the system to roll. So circular blades with a sharp edge all the way around that as the drill cuts down, they kind of roll and allow the system to move. So this also means that the kind of lever arm blades can go in and out as the diameter changes. Yeah.
Are you controlling the width, or is it sensing pressure and adjusting itself?
It's a purely mechanical drum system, so it's all doing that based off the stiffness of the strings, which is something that I could change out throughout the field program. So yeah, so the size of the blades, stiffness of the springs, and pretty much everything is adjustable and relatively easy to change in the field as well. So it's kind of, yeah.
Very cool. And then your other one where you had the little core coming out from the side, the little corer. What propels the drill out?
Yeah, so you can see up the top here, you've got these kind of little black boxes with cables coming out of them. So they're pretty much the smallest linear actuators that I could find. So they have tiny motors which convert the rotation into linear extension. So they have cylinders that get pushed out, and in here, there is the pivot point. So these extend out, and the system gets drawn down. So motor drives rotation through these spur gears, but the core barrel is keyed all the way along the system, which allows it to extend out while it's rotating. Yeah.
And what was its
The
what's its reach?
the expansion of the whole system.
Yeah,
So,
I mean, how far could the drill extend into the whole wall?
yeah, so the aim was to be able to collect a sample that was 100 mil long. So if different factors that would influence that, so with the shape of the boreholes, if it is not irregular, if it is irregular over the length of the system, that could impact the length of the sample. But the overall extension out is constrained by the diameter of the borehole. So I only had 125 mil to design something within, and this length is using absolutely as much of that as physically possible. So I did some modelling to kind of determine what the best angle of sampling was to get the most volume. But yeah, so just for this system, for the size, it's around 100 mil onto length, yeah.
Yeah. Super cool. Another question.
By the way, did you meet Dan? He's one of our drillers, so.
Oh, awesome.
Did you experience any refreezing issues? Like how did it stay warm?
Yes, so I'm not sure if I actually mentioned this, but we were just doing testing in dry boreholes. So after we had gone past the burnt ice transition, we bailed all the water out, mostly to reduce the complexities when we're just doing the initial testing, so we don't have to deal with electronic pressure housing issues. But the ice was around -20 here. So we left the boreholes kind of freezing overnight and for any water to percolate back out through the fern into the borehole. But in some of the cores we got, you can see quite a distinct change in the ice properties. So this system, we were collecting samples up to 1 metre long from the bottom of the boreholes. And you can see a few kind of mil centimetres in some cases of free frozen drilling water and meltwater at the top of the core. and then it goes straight into your glacial ice. So that is it's quite clear in terms of the microstructure and analysing the grain properties of it. It's very distinct change.
How deep were the boreholes?
So we only did testing up to 40 metres. That was mostly limited by manpower. Because you can see here, we didn't have the electronics integrated with a load bearing cable, purely because it's sunk cost. If it's not going to work, you don't want to spend thousands of dollars on it. So now that we know it does, we can make those adaptations. But that also meant we were limited by lowering and raising the system by hand.
Yeah.
So we got we aimed to test at 60 metres, but we had some complications with hot water drilling that meant our borehole had some refreezing, so the whole system didn't actually fit down. But theoretically, once it's been integrated with a load bearing cable, there is not as much limitation on it. But yeah, that was purely a timing, physical standpoint.
What happened to the fluid? Did it just get sucked into the foam?
So the drilling water?
Yeah, the hot water.
Yeah, so in the upper, around like 15 to maybe 18 metres, pretty much all of the water that we drilled with percolated out into the firm. And overnight, some of this would flow back out into the borehole. But after that transition point, it kind of kept filling up. So it would be a constant level of water in the borehole until it could flow back out. But we would always recover a lot more water than we drilled with, so we would be able to recover most of the water as well. Yeah, is that?
So you were sucking the fluids out of the hole to keep it dry?
Yeah, so this is just a kind of off the shelf pumping system, but it was limited to 50 metres head.
Yeah.
Yes, sir.
In the drilling on the surface down there, did you happen to do any geophysics surveys around the borehole after drilling to see if there was any change in signal from water movement?
Yeah, we didn't, but I think that would have been a really, really interesting idea to look at the effects. We have multiple televiewer logs from different stages of the drilling, but that doesn't really tell us much about the properties as they change outward. So yeah, we're getting some of our TM results back later this week, so hopefully that can help inform, but yeah, nothing directly after, so it'd be quite a cool way to look into it, especially for the drilling this year.
I asked because I'm trying to remember, Zoe Corbell and I collected data on McMurdo Ice Shelf in 2016. We had a paper published, and we found a site that was really interesting, and we were really confused about it. And it turned out it was the site of the Andrill site, and you can see the impact of the Andrill site in the subsurface that probably did have. The Andrill was a sub bottom sediment drilling, but I think they used hot water drilling at the surface to kind of get down through, and it resulted in this layer that showed up laterally and kind of spread out and infiltrated at greater depths as it worked its way away from the borehole. And then the other thing that was interesting is you could see these flexure points that seem like Andrill actually impacted the ice dynamics of the area just by the infrastructure there. You could see these kind of rollers downstream of it that looked like there were like flexure points on the ice. So it might be interesting to kind of go back to the site and see if you can see stuff like that.
Yeah, definitely. I don't know the exact figure you're talking about. It's really, really interesting stuff of the effects there. So we weren't going through the whole ice shelf, we were just kind of near surface. So hopefully it doesn't have as much of an effect. And it's a lot smaller system. But yeah, definitely it would be interesting to kind of do a repeat, especially like radar surveys after drilling, because we just did that in the early season before we drilled.
Yeah, I was thinking from that point of view, after you turn taco into Swiss cheese with hot water,
Yes.
you might have to think about where your radar surveys are after that.
Well, so one thing John, I don't know if you want to raise your hand. John Lehman's here, he's gonna be building some down borehole sensors for us for the hot water drill that Jake's working with, and Jess is gonna help Jake with kind of putting brains together, so we'll have some pressure sensors down borehole for the holes that we drill for North Basin and potentially OC Basin. To kind of have a time series of changes relative to the geophysical observations we're making. So, yeah, fun stuff.
So, thank you guys for listening.